So, so we talked about the joint probability, and we talked about conditional probability, as well as an interesting example last time on vaccination, right? Not vaccination, like a rapid test kit. Okay, rapid test kit. And so today we are going to continue this topic, but before that, okay, just want to remind you, okay, I have uploaded the homework 1 to the class, to the E-class already, right? Okay, please don't download it and work on it. But in addition to that, there's one moment. I believe. This one. There's so before we continue the lecture, okay, just want to show you this thing. There's a EMI. Okay. There's an EMI questionnaire that the school has to collect. This one, okay. The first one is what you guys need to answer, okay. The short URL is here. The QR code is here, okay. I understand that. I mean, this is, you guys may not. If I don't give you some motivation, you guys may not answer this questionnaire, okay? So I will include this one in homework 1 as a bonus question, okay, for 20 points, okay, 20 points. So yeah, I mean, I will have the student upload this to E-class for you guys, okay? Whoever answer this one, okay, before the deadline, okay, I believe deadline is maybe about a week into March, so we still have about a week, okay, to do this questionnaire, okay? So you should have plenty of time to finish this questionnaire, okay? This is just for the EMI purpose, okay? So anyway, yeah, I mean, you don't have to take photos, anything like that. I mean, because I'm going to post this on E-class. It's just, yeah, you can just take time to get this done. Oops. So that's well, can be considered like bonus for the homework 1. Okay. So let's go back to where we left off last time. Okay. So one interesting that you may observe, like from the example that we the rapid test key example, is that, okay, what we are given is something like this, okay, on the condition of set phase, okay, on the condition of the set phase, and the the true the positive, like a probability of positive, and the condition of the happy phase, the probability of the positive, okay. You see on the condition here, on the condition of either happy phase and sad phase. The happy phase and sad phase are used as the condition side of this probability, right? Okay, but what we are asking at the end, okay, what happened in the condition is the positive and it's a sad phase, but you get the idea. The phase expression, okay, is no longer appear in the condition part. It appear in the other side, right? Somewhat like these two fields are somewhat like switched, right? Okay, so the previous one and this one, okay, this switching is actually much more important than you may think, okay? So, well, where is it? Okay, here. When the row variable represents data value and the column variable represents parameter value, remember what I told you? Okay, if you have a model, that model has parameters. Remember? And that parameter sort of control that model. Okay, if you still remember, I gave an example like Gaussian distribution. Okay, the variable that control Gaussian distribution is the mean and the standard deviation, right? So there are many mathematical models, okay, that have like parameters, okay. So think about this. If one dimension, okay, let's consider this joint probability, okay. Joint probability has 2 dimensions, right? Okay, if one of the dimensions represent data value, okay, and then the other dimension, okay, represent the parameter for the model, then what happens is like this, okay. You are given, this is what you are given certain parameters, okay, because your model, original, you already have the model. So given certain parameters of that model, and the probability of those, of the data you collected, okay, when this entry, okay, these entries are given. And also, you have the prior. The prior is actually the probability distribution of the model parameters. Okay, so these two things are given. This is we also have this in the rapid test kit example. I just forgot to mention. Okay, here, where is it? Okay, there's a test for disease. That disease is, sorry, not that one. This one. This is a rare disease. Remember, we talked about rare disease. The rare disease, the probability of the rare disease, okay, because that disease, okay, can be found like 1 out of 1,000, right? 1 out of 1,000. So the probability of the sad phase, okay, without any condition, probability of the sad phase is 0.001. Remember? That's we are given this one, right? This is 1 out of 1,000, right? As well as this, it's here. Yeah, we are given this one. We are given this one. We are given this one, right? So this is probability distribution of the parameter value, okay? Of course, this is a simple case because this is really not a distribution. This is really like we are given this prior probability of prior value already. But because this is like a real, more like a discrete case. So it's relatively easy. But okay, you can imagine this is like this is a prior, the probability distribution of the parameter value is given. Okay, so it's like what I mentioned. Okay, so you have this one. You have this one, and what we are interested is to compute, okay, on condition of the data value, on the condition of the given, of the collected data value. What is the probability distribution of the parameter values? See? These two things switched, right? So what happens like this, okay? So okay, you believe in something like remember like okay, when for example like you believe in like the weather, okay? The weather is in Zhongli, okay? Remember we talked about the cloudy example, okay? If your prior is like okay, it's represent like the chance that Zhongli is clouded, okay, is maybe 40%, but okay, so that's this one. This is your prior. Okay. And now you collect the data. Okay. the data is, well, maybe you see like somebody tell you it's raining, right? Okay, so this is the, well, based on the current parameter setting. But of course, in this example, the parameter, the Zhongli has 40% of the cloudy weather. It's not really, has not played any like a role in like you collect data like, wow, somebody tell it's raining. I mean, the chance of the cloudy, okay, from the prior, okay, it doesn't affect the probability of the, well, the thing you collected. Like, well, it's raining, but based on this value, okay, you know it's raining. You have to adjust. You have to adjust your parameter value, your belief in parameter value, accordingly, right? Remember I told you the chance may be 90% raining, right? I mean, it's no longer 40%. It's based on the observed data. So this is exactly the inference. Okay, this inference is based on, it's originated from the prior, and it's based on the data, because the data, you are conditioning the new belief based on the data that you collected. Okay, so this is the the Bayesian inference, the most important aspect of the Bayesian inference, and this is why how the Bayes rule, is applied here. Okay, so if you draw a table, it's going to look something like this. On one dimension, you have the data value. On the other dimension, you have a model